So I want to welcome everybody here to the Physics Colloquium. Our speaker today comes from the University of Arizona and from Brookhaven National Laboratory. He has a joint appointment. This is one of these neat things that the RECAN Brookhaven Center does to make it possible to hire somebody at a university for half price, I guess. And eventually a dean has to pick up the other half. I think that's the other part of the story. So anyway, so right now he has flown here all the way from New York, but normally he would fly here from Tucson. He got his PhD at the University of Cambridge in England in 2010, and after that went out for a postdoc at the College of William and Mary for a couple of years, and then took a postdoc at MIT. And his specialty is high energy theoretical physics and also nuclear physics. He does his work doing computation mostly, and lattice gauge theory, which is the kind of stuff I do. So I hope you'll enjoy his talk. And he's giving the talk that I would probably normally have to give, so I'm glad that he came here in order to do this for us. So without further ado, Stefan.
Yes, turned it on. So, I'd like to thank Carlton for the very kind introduction to this colloquium, and it's really nice to see him. He's also one of the authors of one of the textbooks on lattice quantum chromodynamics that I've been using extensively. So today I would like to tell you about some very interesting hints for physics beyond the standard model that have been observed in decays of beauty quarks. And some of those were reported on various blogs and news web pages, such as in 2013 when LHCb released new experimental results on one particular decay of a B meson, and I'll explain to you what that is, that deviated from theoretical predictions based on the standard model, and got people excited. But before I want to go into those hints for deviations from the standard model, I'd like to take a step back and tell you a bit about the standard model. And I want to do this by going a bit through the history, actually, showing you how in the past also surprising experimental results led to theoretical advances and led to the construction of the standard model of particle physics. And so basically I want to start by telling you about flavors of quarks. Those are the up, down, strange, and so on, and how the weak interaction changes can change flavors, and then move on to colors of quarks, which are of course related to the strong interactions. And in that section, I'll also tell you a bit about lattice quantum chromodynamics, before I then finally come to these beauty quark decays. So shown here is an early history of discoveries of hadrons, starting with the proton. And this is followed by the neutron around 1932 or so. But then in the 50s and 60s, there was an explosion of new discoveries of particles that were observed to be strongly interacting with each other. And some of those particles also were surprisingly long-lived, given how strong they were otherwise interacting when they were being produced. And those were called strange particles. So for example, the kaon and the lambda are strange particles. And Gell-Mann and Zweig then realized that this pattern of all these of this zoo of strongly interacting particles can be explained in a nice way if you think of them as being made out of three basic new elementary particles, the up, down, and strange quarks. And then you get these nice classifications of the observed states in terms of the isospin, which is defined here, related to the number of up and down quarks, and the strangeness, which is related to the number of strange quarks. In addition to the strong interactions, the weak interactions were also, of course, studied at that time. And weak interactions affect both leptons, such as electrons and neutrinos, muons and their neutrinos, and these hadrons. And even though this Cabibbo did not yet have this understanding in terms of quarks, he realized that the weak interactions of leptons and hadrons could actually be described by a universal theory that had this coupling strength G, which determines the probability amplitude for such transitions between different flavors of particles. And in the case of the quarks, there is an extra mixing angle involved, which we now call the Cabibbo angle. So in such a way that transitions from up and down quark have a probability amplitude G cosine theta, and up and strange G sine theta. And this was basically realized by looking at all kinds of combinations of initial and final states. And one very important system, very important for the development of our current understanding of particle physics, is the system of neutral kaons. So those are mesons made out of down quarks and anti-strange quarks, or they are antiparticles. And as shown in this slide, the weak interactions through such a second order process can actually change a neutral kaon into its own antiparticle, and you get these oscillations between those states. So in this Cabibbo theory of the weak interactions, this oscillation frequency was then calculated and found to be very high. But the experimental data showed actually a much, much slower conversion from neutral kaons to neutral antikaons, so much slower oscillation. There was some first contradiction at that time with this theory. And Bjorkin, Glashow, Iliopoulos, and Mariani then realized that this behavior can actually be explained in a natural way if there's, in addition to the up, down, and strange quarks, also a fourth quark in nature, the charm quark. And if the weak interactions are such that transitions from charm to down quarks come with G, a probability amplitude of G cosine theta, and transitions from between charm and strange quarks with a probability amplitude of minus G times sine theta. And then this can actually be understood as a nice rotation matrix in this basis of quark flavors, which still is just parameterized by this Cabibbo angle. Now, if you now look at all the allowed processes contributing to these transitions from neutral kaons to neutral antikaons, and as always in quantum mechanics, if you don't observe the intermediate states, you have to sum over all paths that lead you from the initial to the final state. And so you need to sum over all these diagrams, and you get now various different factors of these couplings for the vertices, where one quark changes to another quark. And according to those rules, that 2x2 rotation matrix, if you add this all up, well, it's complicated because the quarks also have different masses. But let's consider for simplicity the case that the charm quark mass is equal to the up quark mass. then a lot of these diagrams are equal up to some minus signs. And if you add up the probability amplitudes, you actually get 0. In that case, you've completely suppressed the oscillations. That's a bit too much. And of course, we know that the charm quark mass is not equal to the up quark mass. But rather, if you want to explain the experimentally observed oscillation frequency, it turns out you need to set the charm quark mass to approximately 1.5 GeV. And then this cancellation happens to just the right degree so that you can explain the experimental result. There was another remarkable experimental result in the neutral kaon systems. Already at that time, it was known that the weak interactions, which are mediated by W bosons and also Z bosons, couple, in fact, only to what's called the left-handed components of particles and the right-handed components of antiparticles. So this refers to the helicity, which is the projection of the spin, shown in red, onto the momentum of the particle, shown with this black arrow. And very important in particle physics are the transformation properties under discrete symmetries, or discrete transformations, namely such as charge conjugation, which changes particles into antiparticles, parity, which is just the spatial mirror operation, and also the combinations thereof. So clearly, because of this property, the weak interactions are not actually, or the theory of the weak interactions is not symmetric under charge conjugation or under parity. But if you look at this diagram, you see that the combined CP changes a left-handed quark, say, into a right-handed antiquark. And those behave the same under the weak interaction. So it was thought at that time that CP, the combined operation, is still a good symmetry for the weak interactions. However, experiments with neutral kaons then showed that CP, in fact, is also violated. This is a bit more complicated to explain, so I won't go through that. But that, in fact, led to another theoretical prediction, namely Kobayashi and Mascawa were able to show that this phenomenon of CP violation can only be explained in a natural way if there are, in fact, yet another two quarks in nature, so that we have three such generations. And in that case, the flavor transition probability amplitudes are described by a 3x3 matrix, which is now called the Kabibbo-Kobayashi-Mascawa matrix, or short CKM matrix. And in quantum mechanics, you really need to describe these actually by complex numbers, these transition probabilities. Now, it turns out that some of these complex phases in these matrices are actually not observable. They can be absorbed into the quark fields. And if you had only two generations of quarks, then you can actually get rid of all of them, and you're left with just a real 2x2 rotation matrix with just parameterized by one angle. However, in the three generation case, this is no longer true, and there has to actually have one complex phase cannot be eliminated from this matrix, and that is ultimately responsible for the CP violation, it turns out. Okay. Now, at this time, still, neither the charm nor the top nor the bottom quark had actually been observed in experiments. So these are all theoretical predictions based on unexpected low-energy behavior in the neutral kaon system. But then, in 1974, a new meson was discovered that was had a mass of 3 GeV, and was very narrow in its decay width. And this was then quite immediately clear that this has to be a bond state of a charm and anti-charm quark. So this is then the experimental confirmation of the charm quark, both at Brookhaven National Lab and at SLAC. Oops, it's just slow. And yeah, so there was also bottom quark discovery somewhere here in 1977. Again, in the form of BB bar bond state, the upsilon particle at Fermilab at a mass of about 4.5 GeV. And in 1995, not so long ago, finally the top quark being produced in proton-antiproton collisions at Fermilab. And its mass, which is about 170 GeV, actually was also already predicted based on, in this case, neutral B-meson oscillation frequencies. So this is a big triumph, of course, for the theory. Let me now move on to the strong interactions described by quantum chromodynamics. So I've showed you how W bosons can change quark flavor. Gluons, however, change quark color, and so the quarks come in these three colors, in these three states that we refer to as colors. And gluons can do that by basically taking away one color and bringing another one back to a quark. And therefore, you can think of the eight gluons, 8 types of gluons that we have in nature as sort of being composed of one color and one anticolor. And you get these 8 combinations. There's also a ninth one, which would be completely colorless, but that is does not occur in nature. Now, just to illustrate how this is happening, so you can draw these kind of Feynman diagrams where, for example, you have here quark-quark scattering, and starting with an initial state of red and blue, and then these colors are exchanged by such a gluon. And because gluons carry color and anticolor themselves, they also interact with themselves, even without involvement from quarks, as shown here. So you get these extra diagrams, and that is what makes this theory so very different from electrodynamics. So, and one consequence of these gluon self-interactions.
Do they really assume any color, or that is just for the representation sake? We just assign them color.
It's just for a representation. Yeah. It's a mathematical construct. And one consequence of these gluon self-interactions is that if you look at how the effective strength of the interactions depends on the momentum scale or the length scale of your process that you're calculating or measuring, what you find is that the interaction, in fact, gets weaker at shorter distances, while the effective coupling strength gets weaker at shorter distances, or equivalently higher momenta, and gets stronger at lower momenta, as shown here in this logarithmic plot, in a region of still very high momentum. And yeah, this property is known as asymptotic freedom, and was proven by Gross, Politzer, and Witschek for the non-abelian gauge theory, which quantum chromodynamics is. But so one consequence is that as you go to low energies, basically this coupling strength diverges. It becomes very large. And related to that is the phenomenon of color confinement, which basically means that there are no free color charged particles in nature. You always have all color screened by forming a bound state that has zero net color. And the dynamical reason for this is essentially if you were to take two infinitely heavy, or one infinitely heavy antiquark and one infinitely heavy quark and place them at some distance from each other, you would get this sort of flux tube forming between them from the gluonic field, and as you pull them apart, then at some point it becomes energetically favorable to have instead this screened by a new quark-antiquark pair, and so this breaks then apart into two heavy light mesons. So, yes.
I remember people were talking about bound states of gluons. I think they were called glue balls or something.
Yes.
Like that. What was the status of that thing right now? That's it. Yeah,
So, if you consider the theory, you can theoretically you can turn off all the quark effects. You can look at pure gauge theory or the pure gluonic theory. Then you very clearly see all these gluonic versions of hadrons, so these gluonic bound states. Now, once you include quarks in the theory, in principle they are also still there, but they can no longer be so easily separated from ordinary hadrons. So there's some complicated mixture, quantum mechanical mixture going on between those. But yes, in principle, those exist.
But there is nothing experimental.
I think nothing very definitive. There are some states that look like they are dominated by the glue ball component. So such states have been observed recently, I think.
Okay.
But it's just not so clean because of the presence of quarks as well. Yes. So. Just very briefly to explain to you what lattice quantum chromodynamics is, I want to go back to the picture of fields rather than particles. And I want to make the analogy with classical electrodynamics very briefly. So you know in classical electrodynamics you have the potentials, you have this four-vector potential, and then you have the electric and magnetic field strength related to them. Now, in classical chromodynamics, the gluon fields are also described by a vector potential, but this now actually comes in 8 copies for the 8 different, corresponding to the 8 different types of gluons that we saw earlier. And one other feature is that the equations already in the classical theory are nonlinear. So you see that, for example, from the fact that the chromoelectric and chromomagnetic fields are nonlinear functions of the potentials, and so these quadratic terms actually now contain the strong coupling constant in here already. So then lattice quantum chromodynamics is basically starts from this classical chromodynamics and quantizes it, and it quantizes it using a version of the path integral. So, as you know, in quantum mechanics, the probability amplitude to go from some initial to some final state can be obtained by integrating over all classical paths or changes of configuration between those states, and integrating the exponential of I times the classical action of that path. A similar version also exists for field theory, where you can calculate expectation values of any combinations of fields by integrating over all classical field configurations with such a weighting factor that contains the field theoretical action of classical field theory. Now, this is an infinite dimensional integral, and to do the calculation, basically one approach is to do a perturbative expansion in this coupling constant. It's a central Taylor expansion, and so what you then actually get are these familiar Feynman diagrams that I showed you earlier. However, because of this property that the strength of the coupling, strength of the interaction grows at low energy, this does not converge actually at low momentum, and it does not, for example, explain this phenomenon of color confinement. Clearly, here you always work with free color charged particles in your initial and final states. So the alternative is, one alternative is to just do this integral by brute force, essentially, without doing this expansion. But to be able to put it on a computer, you have to make this a finite dimensional integral, and that can be achieved by first defining these fields only on the points or links of a space-time grid, and writing
that
down.
real space, I mean 3 dimensions of time? It's not some multi-dimensional space.
That's correct. It's
Okay, that's a
it's space-time. So there's these extra color degrees of freedom, but the lattice is really just space-time lattice. It typically has a spacing of around 0.1 femtometers. And
The
it's
real femtometers.
real femtometers, it's a real thing. So, and it's a few femtometers across, a couple of times the typical size of a hadron, for example. So to be able to write down this discrete version, one also has to approximate the continuum derivatives, for example, that are in the Dirac equation or the Dirac action by discrete versions and so on. And I don't want to go into too much detail there, but this was formulated for Chromodynamics by Ken Wilson in 1974, and Mike Kreutz at Brookhaven National Lab actually in the 80s pioneered the first real numerical simulations actually doing these integrals on computers, and since then this has become an extremely powerful tool for doing first principles calculations in quantum chromodynamics without having to expand on a small coupling parameter.
What's the era of that computer? What are you? 19 what?
No, it's pretty recent.
It's
This
pretty
one-
recent. They're still making big computers like that?
Yes, this is
I
this
thought
is,
we used billions of computers rather than one big one.
the problem is that they all need to talk to each other very fast, so therefore they want to stick them into one room and connect them with cables. I actually used this particular computer for some of the calculations that I'll show you later.
How do you know?
This one is at question. I was never physically in that room.
You
so-
watched your lights flashing?
All right. This is at Texas Advanced Computing Center. Okay. And so I should say such an integral numerical integration is done actually by Monte Carlo methods with importance sampling, and you're sampling essentially you're sampling field configurations, gluon and quark field configurations. This is just a nice picture showing one time slice of such a gluon field configuration on a lattice with 32 points in the spatial directions. And this is the action density being visualized here.
And how big is the time slot?
Excuse me?
How big is the time element?
The time length is 96 points with the same spacing in terms of femtometers, so you can convert this to time by dividing by the speed of light.
Okay, I can do that.
Yeah.
Oh.
All right. But now we formulated this discrete theory, which is still an approximation to the real world, but it's one that can be made arbitrarily accurate by making the lattice spacing as fine as you like. And so typically what one does is one performs the calculation with a few different values of the lattice spacing and then looks at how strongly the results depend on that. If it's fine enough, you don't see much dependence on the lattice spacing, or usually we then also extrapolate to zero lattice spacing or our numerical results. You also need to extrapolate to infinite volume, of course, ideally. Okay, so let me just briefly show you some predictions from Lattice QCD, or post-dictions also. Shown here are Lattice QCD results from the so-called BMW collaboration from 2008 for some well-known hadron masses. And the blue points actually used those experimental masses as input just to set the correct quark masses in the computer and to figure out the lattice spacing. And then all the red points are predictions coming out of the computer compared to the experiment, which agree nicely. And well, in this case, they are post-dictions. But here are results from a calculation that my collaborators and I did last year of baryon masses of baryons containing various combinations of charm and bottom quarks instead of just up, down, and strange. And only those with the black bands have actually been observed in experiments so far. All the other states are predictions from Lattice QCD. In fact, this one has since been observed at the LHC.
Do these predictions come with production rate predictions in accelerators, or can they determine that?
That's much more difficult. So the answer is no.
Okay.
Okay, so after that introduction, let me now really come to the search for physics beyond the standard model. So first of all, why do we even want to keep searching? There are broadly two reasons. One is that there are a number of unexplained phenomena in nature, most of them in fact from cosmological or astronomical observations, such as the existence of dark matter and inflation and dark energy, and also the matter-antimatter asymmetry of the universe. And then the other reason is that there are certain theoretical arguments or considerations of beauty or elegance of the standard model that would lead you to believe that this cannot be the whole story. So there's, for example, this hierarchy problem that is related to the Higgs mass, and naively, if you calculate quantum corrections to the Higgs mass, you would expect that the Higgs mass is at the Planck scale. So there's some enormous fine-tuning or some new some new fundamental physics that cancels those quantum corrections to some extent. And then just the fact that we have this weird pattern of all these particles with some weird hierarchy of masses and couplings and so on. So where do all these values come from? There's also the strong CP problem and various other arguments. And so how can we search for a more complete theory? Well, one way is, of course, to directly create new particles and energy collisions, such as what was now achieved for the Higgs boson. But an alternative way, and a way that I described in the beginning, really in the history of was very successful, is to look at unexpected behavior in low energy processes that still are sensitive to the effects of the existence of heavier, previously undiscovered elementary particles, which contribute as virtual particles, as intermediate states.
At the very beginning, I kind of reluctant to ask, how do you observe the oscillation of a neutral kaon? I mean, is it observable in the cloud chamber? How is it one of those big things in Large Hadron Collider that they detect the path?
That is a good question. I think you look at their decays into pions, and this was in a very small scale experiments. Very small particle accelerator experiments where this were produced, and maybe someone else in the room knows more about this.
Should be Gordon.
So, yes. Well, one should also, of course, continue these astronomical observations that already show us lots of evidence for physics beyond the Standard Model. And so, historically, looking at flavor-changing transitions was very successful. So, let's keep doing that. And so we know that if you're looking at quarks, then we have these flavors, and their transitions are described by this CKM matrix. And so the questions that you could ask is, are there any new bosons besides the W boson that can change quark flavors? Or can quarks change into something else? Is there a fourth generation? Those are questions that you could ask. And one way to test this is to test whether indeed this description using this matrix is successful. And to do that, you can test, you can basically measure the elements in that matrix and test, in particular, the unitarity of this matrix. The unitarity is essentially conservation of probability, so if quarks could change to something else, you would get some non-unitary matrix. And let's focus, for example, on this component here. So unitarity, this is what unitarity means. And so we can test, for example, this particular relation involving this set of matrix elements, which is usually phrased in this form by just dividing by this middle number here. So it's the sum of two complex numbers and 1, which should equal 0. And this is the complex plane. And shown here are various experimental measurements that give constraints on the angles or side lengths of the triangle, which corresponds to this sum of three complex numbers summing up to 0. So here's R1, and then here are the other two complex numbers. And if you sum them to 0, you should, if they sum to 0, then they're described as such a triangle. And the idea is to measure many different flavor changing processes and get constraints from them, and then see whether there's some region where all of these constraints overlap. That gives you, that would show you the consistency of the theory. And the hope is, of course, that by making more and more precise measurements, we actually find inconsistencies. But at the moment, there's still this region where everything overlaps. And let me now focus on this particular constraint shown in dark green here. This comes actually from a measurement of this CK matrix element VUB, which is the smallest element in that matrix, and is also the least well known in terms of its relative uncertainty. So how can we measure this magnitude of VUB? One way is to look at the decay rate of a B meson containing a B quark and a light antiquark to a pion and a lepton, which could be an electron or muon, say, and its antineutrino. And then the differential decay rate of this process is equal to the VUB squared that we want times some matrix element in quantum chromodynamics, which we don't know, but which we can calculate in Lattice QCD. So this matrix element describes essentially the effect of the quarks being bound inside the hadrons. So that modifies a bit the decay rate, and this matrix element is called a form factor that needs to be calculated if we are to extract VUB from experimental data for this decay rate. Now the experimental data have until recently essentially come from these two experiments, which are E plus E minus colliders producing lots of B mesons and anti-B mesons. So these are called B factories. And the experimental data are shown here as a function of momentum, essentially, for this decay rate. So, let me explain to you a little bit about this Lattice QCD calculation that goes into there. So we have this matrix element of this what we call a current, or which is a product of these anti-quark field operators, and these subscript L actually indicate that those are just the left-handed components, as we discussed earlier. Now, this left-handed current can actually be written as a difference between a vector current and an axial vector current, as shown here. And it turns out that for this B to pi decay, the matrix element of the axial vector current is 0, just by parity symmetry, and the matrix element of the vector current is described by these functions. Can be parameterized by these functions conveniently, which have been calculated on Lattice, including by Carpenter-Tar's collaboration, as shown here. From this is not the latest. These are not the latest results. This is a calculation from 2009 for this matrix element. And then one can convert this matrix element back into the decay rate, and one can do a joint fit of the experimental data and the Lattice data shown in magenta here, where this proportionality factor between them is the fit parameter. That's our VUB that we want. And so, as of 2013 or 2014, this was the number that was obtained from this decay process. And this is again shown here with this blue data point. Now, there's in fact another way that this has been done, also with B meson decays, but instead of just looking at pions, you don't reconstruct a particular hadron in the Vual state. Effectively, you're summing over all types of running states that contain an upquark. That's called the inclusive method. And in that case, actually, you can get around having to use Lattice QCD. So you can use different theoretical methods to extract VUB, but what you get is actually higher, and it differs by about 3 standard deviations. This is the situation as of 2014. Now, there are lots of things that could have gone wrong there, but one interesting possibility is that there is indeed a physics beyond the standard model explanation for this. And one way of coming up with such an explanation is the realization that, like I said, the b to pi decay depends only on the vector current, but the inclusive extraction actually is sensitive to both the vector and axial vector currents. And so you could imagine that there's some new interaction, let's say some new boson W prime, which could be very heavy and could have been still remained undiscovered, that could contribute through quantum mechanical interference to this decay. And this actually then could effectively replace this vector minus axial vector structure by some new, more complicated structure that has some extra right-handed component, or right-handed means vector plus axial vector. And so in that theory, you would have this parameter VUBL and then this epsilon r. And if you look at the VUBL and epsilon r plane, then the experimental data for the inclusive measurement and the b to pi decay give you those allowed regions at, this is I think just 68% confidence level. And there's actually some overlap here where you could explain this in principle using this new theory. So how do we go from there? These b-factory experiments are no longer running, but the LHCb experiment has entered the game also now. And it turns out that at the Large Hadron Collider, where you collide protons and have much less knowledge about your sort of initial state, also much larger backgrounds, this b to pi decay is quite difficult to analyze, and this analogous baryonic decay, which is lambda b to proton and lepton and antineutrino, as shown here, actually is slightly easier to analyze experimentally, the proton offering a more distinctive signature in the daytime. So, on top of that, this process, this baryonic decay, lambda b to proton, actually also has the property that it's sensitive to both vector and axial vector current. So it could give us some new information on this puzzle. In this case, these matrix elements are described by 6 such form factor functions, which my collaborators and I recently calculated using Lattice QCD. And this is just these are just results for one of them as a function of momentum. And these data points, we call them data, even though they're theoretical calculations coming from a computer.
I consider them experimental.
These are then fitted by some smooth function that also actually includes some extrapolation to zero lattice spacing and some extrapolation actually in the quark masses to match exactly the physical quark masses. And then again, those are all of those 6 form factor functions that we need in the baryonic case. Taking them, we can then predict the differential decay rate divided by this VUB squared. That's something we can calculate. That's a pure QCD quantity after, essentially. That's our prediction. It's uncertainty band as a function of momentum. And LHCb, amazingly, we're able to measure this. And their signal is shown here in blue. So this is a different kind of plot. This is some kinematic variable, this is the number of events, and this is some fit that they've done. So let's not go into the details. But let me now jump back to this, those constraints on this theory with the extra right-handed coupling. This was just the situation that we had with the mesonic decays. And voila, here's the new constraint from the baryonic decay, shown in green. There's no longer a region where there's all overlap. And there's still this unexplained discrepancy with the inclusive B-meson decay, but both exclusive methods, now mesonic and baryonic, agree with each other and with the standard model. So it's certainly a bit unfortunate, but you see that this baryonic decay is very useful to give you new information. So I'd like to, in the last 5 minutes or so, mention two other processes where there are certain tensions between theory and experiment. This one is actually still very similar. It's also a decay of a B quark through a simple W boson exchange. But this time we're looking at B quark going to charm quark, lepton antineutrino, which means a B meson decays to what's called a D meson, D as in charm. And what was measured here is the ratio of the decay rate where you're looking at the final state with tau leptons versus the decay rate with the final state with muons. Now this ratio can be calculated very precisely because a lot of the QCD uncertainty cancels actually in this ratio. And here are experimental results. I should very briefly say that there were measurements for two different types of D mesons with different quantum numbers, one called D and the other one called D star. And therefore we have this two-dimensional plot of this ratio of these experimental results for this measurement for the D mesons and the D star mesons. So these ellipses, black and blue, are measurements from Barbar and Bell of both of those quantities, and LHCb has just measured RD star, as shown in cyan, and if you combine all experimental data, you get this red ellipse. Now, the standard model prediction is done there. It's actually a 3.9 sigma discrepancy. The theory here is quite solid, but the experiments are very difficult, I would say. So, nevertheless, it has been suggested that this could be a hint of, for example, a charged Higgs boson, which could explain why the final state with the tau leptons receives an excess. So the Higgs boson couples via the coupling strength is determined by the mass, and these tau leptons are much heavier than so this is essentially only relevant for the tau final state, and could explain this excess. Again, it will be interesting to see the analogous measurement with baryons, and we have predictions for the analogous baryonic decays with muons and taus, and for the ratio of the total decay rates. That's very precisely predicted, and the LHCb collaboration is working on a measurement, so it would be very interesting to see if there's also an excess in this baryonic decay. So the last type of process is a loop-mediated process where a B quark changes to a strange quark. Those both have the same charge, B and strange, so we are exchanging, for example, two W bosons here, some other intermediate particles running in a loop. And in this case, for example, one of the processes that was being looked at is the decay of a B meson to something called a K star meson, and mu plus and mu minus. And this is only one of the diagrams contributing to this decay. There are many. So, in this case, the K star is actually itself unstable, and it decays through the strong direction into another type of kaon and a pion. And the experiment has analyzed also the angular distribution of these decay products. Now, in this plot are some complicated observables describing the distribution of the angles of the final state of this decay process. Also, as a function of momentum, then these are the angular observables. But essentially all you need to see is that in blue there are some data from LHCb, and in gray there are some standard model predictions, and there's some tension between them. And there is some way of getting better agreement of the data, and this is by shifting away one parameter that describes essentially the strength of a certain class of diagrams contributing to this decay, by shifting away this parameter from its standard model value. So this is shown in red. Shortly after that, my collaborators and I did, with the help of a Lattice QCD calculation, looked not only at the angular distribution but also at the overall decay rates, as shown here. Shown in cyan are our predictions for the decay rates calculated in the standard model, and the data points of the error bars are the experimental data. And so in this case, the experimental data are actually below the prediction. Seems to be some deficit in the decay rate. But interestingly, if you change this one parameter called C9 in the same way as it needed to be changed for these angular distributions, we also get a better agreement with the overall rate for this decay. And a similar effect, a similar deficit in the decay rate was also seen in this decay B to K, B plus or minus, where you have this pseudoscalar kaon instead of this vector K and K star in the final state. This is a calculation that again was worked by and his collaborators. And what's more, so all of these previous tensions were seen with the muon final state. And so the experimentalists also looked at the ratio between the muon final state and the electron final state for the decay rate. And they looked, in this case, because the muon mass is also still relatively light for the momentum scales that we're looking at, this ratio is actually predicted to be extremely close to 1 in the standard model. The muon mass and electron mass can both be neglected practically in this kinematic range. The muons and electrons in the standard model don't differ by any other property other than their mass. So this should be 1. But the LHCb measurement was found to be significantly, 2.6 standard deviations below 1. And interestingly, if you change this parameter C9, but if you assume that this change only applies to muons, actually you get a pretty good agreement again with the data. So, there are various possible models that again could explain this, although these models are not particularly pretty. So you could have a new Z prime gauge boson that, unlike the Z boson in the Stein model, actually can change quark flavors already in this 3-level way. But I noticed a very interesting paper just, I think 2 weeks ago, where these authors came up with a lepton quark particle that actually can explain these effects that I just described with the flavor changing neutral current decays in the E to K sector, and it can also explain these charge current decay anomalies of the taus in the final state. And furthermore, it can also explain the tension between Stern model and experiment for the muon anomalous magnetic moment, and all of this with the same parameters, and just one extra particle. So that's, and here's how they do it. This lepton quark can nicely contribute to all of these processes and can somehow explain all of this. But still, it doesn't really solve any of these fundamental questions that I referred to earlier that motivated our search for new physics. So it's kind of very strange at the moment. And again, also for some of those flavor chain neutral current decays, the baryonic decay will give you new information. But here's a very preliminary result for the baryonic decay rate, lambda b to lambda mu plus or minus, where, I'm sorry to disappoint you, but we actually have indications that we again get something that looks inconsistent with the mesonic sector. So here there's some hint of an excess in the decay rate, whereas in the mesonic sector there is a deficit. And at least this simple way of explaining it with a simple change in just the C9 does not work in the baryonic case. So maybe it's just that we don't fully understand some QCD effects contributing to this decay. It's actually very likely in this case because there are certain things that I didn't tell you about here in the QCD calculation. Of course, there's a prospect of a lot more experimental data. We are just about here in terms of data from LHCb, and this is the expectation for the next 10, 15 years or so. So let me summarize. We think that our understanding of fundamental physics, as described by the standard model, is still incomplete. And as demonstrated by the historical developments and also by the current tensions that we're seeing, big quarks and looking at flavor changing decays of big quarks is a good way of searching for new effects beyond the standard model. And this requires crucially input from Lattice QCD to deal with the strong interactions in those processes. And we've seen that there are already some interesting tensions or anomalies in decays, mostly in B mesons, and that now, thanks to the Large Hadron Collider, we can also look at baryonic analogs of those decays and get complementary information. And so the hope is that by combining future experimental data with also improved theoretical calculations, we can further pin down these deviations, and hopefully some of those will turn out to be something real and some real sign of new fundamental physics. So thank you.
So Stefan gave a much clearer talk than I possibly could have given. And now we will take questions from the audience.
Yeah, I take it that quantum chromodynamics on this, what do you call it? On this digitized thing.
Yes.
That's absolutely established, and nobody's questioning it, and that's fine with me. But it still gives you a lot of space in which to work, and it's hard to find the right problem to solve, isn't it? I mean, how do you know the calculation that you're doing is the one that's going to liberate everything?
You mean that's going to explain this?
That's right. I mean, how do you know before you did it?
So
Pays your money and takes your
we don't.
choice.
We don't.
Huh?
You pay your money and take your choice.
Well, I'm paying money, but okay.
So those are just one ingredient. Those calculations are just one ingredient in the process of understanding those deviations. And they are, the lattice QCD calculations are a reliable way of dealing with just the strong interaction contribution to some of those processes. There are actually certain processes where we still currently don't have enough computing resources, or we have other theoretical problems that restrict us from calculating certain processes that we would like to calculate. But we understand very well what are those restrictions, and we have Lattice QCD really has controlled uncertainties. We can change the lattice spacing and see how much the numbers change and so on and so forth. But of course, there's a lot. Yes.
You said that we'll find that showed that you use the path integrals.
Yes.
And do you use quantized, discretized, numerical methods to
Yes. So in fact, so what we want to do is we want to generate points in our integration space, essentially. So we want to do this important sampling of these gluon field configurations. And one way of doing this is which almost everyone uses now is called the hybrid Monte Carlo algorithm, which involves some evolution of these configurations in the simulation time, and this evolution involves integrating basically the classical equations of motion. So that's also called molecular dynamics, and for that there are various types of integrators that are being used.
It just seems that, you know, for an individual who wanted to play with this sort of thing, you need the big resources of a supercomputer or cloud computing or something in order to do the Monte Carlo, because you have to select and isolate, you know, millions of random values, right, in order to perform the algorithm. But if you use, you know, an iterative method of some sort to just, you know, play, like, supposing you wanted to generate a screensaver of the interaction, right? And you needed something that would be simple and, you know, less precise, but would give the flavor of what the interactions were, right? So would you, you know,
Yes.
could you use I mean, or is it just so blurred out that those other methods don't work and it just takes too long to do any calculations at all?
So I think we are already using what we currently think are very efficient methods. But if you wanted to, as you say, if you just wanted to get a flavor of what's going on, you could just make the lattice relatively small. And in fact, even on a laptop, you could do simulations that are not completely off. Because this is a four-dimensional lattice, and the computing power that you need grows really very rapidly.
Sure, exponentially.
Size and
so when you say a smaller lattice,
you could just use a small lattice with a coarser spacing, or you could turn off the dynamical quarks. That makes it a lot cheaper, and you can run this on a laptop just to play with it. Yes.
Let's give some other people an opportunity.
Yes. Yeah, so I had a question. It's actually Charlie's question. When you did the form factor calculation at the height q-squared, it didn't seem like it fit very well. Can you explain this?
This you're probably referring to this plot.
Yes.
Yes. So as shown here on the left, these simulation results are actually at two different lattice spacings, and also they are actually done with up and down quark masses that are slightly heavier than in nature. And we basically tell you what our up and down quark mass is by telling you what the corresponding pion mass is that we get from the calculation. This is shown here. And this curve is actually not directly a fit to the points that you see here, but it is obtained from a much more complicated fit that includes terms depending on the lattice spacing and depending on the quark masses. And it is obtained by then evaluating this fit function for zero lattice spacing and for the physical value of the quark mass. So this is why the curve is shifted away from the points, because it is not meant to go through these points. It's evaluated in a different, for different set of
There's no experimental data.
Right, but I mean, you could imagine doing a fit to the various results.
It is
in fact, I'm sure you do fits to do the projection down to a equals 0.
John?
Yeah, so for this lattice QCD calculation, so I was wondering, how do you determine the initial condition, and how do you determine when to stop? Like, what you need the system to reach some kind of equilibrium or something?
Yes. So I think the initial condition is not very important, but typically one would start with just a random configuration where these I should say I have not generated these myself. The nice thing is you can actually download these configurations from large archives and then use them to do calculate your observables, do your perpendicular using them. But my understanding is that you could, for example, start with a random disordered configuration and then start running this evolution that you know has the correct equilibrium distribution. Now, so you need to decide when have you reached this equilibrium range, when have you sort of normalized your Monte Carlo, and you do that by looking at the evolution of certain observables as a function of simulation time. For example, one very easy to calculate observable that you could look at is called the plaquette. That would be just a simple gluonic observable that depends just on the gluon fields on one particular link on the lattice. One closed loop made out of 4 links of the lattice, multiplying this together, taking a trace of that. You look at how that evolves and you look at how other observables evolve. And so you discard some time range until you've reached this equilibrium stage, and then you need to just run long enough so that your statistical uncertainties from the constant fluctuations get small enough in the average that you're then calculating over those configurations.
From the diagrams you have shown, I have a general impression that the error bar of experimental data actually is much bigger than the QCD or standard model predictions. So my question is, how long do you expect it would take for experiments actually to improve their accuracy, so that we can make sure whether there's really a difference or not? 10 years or 5 years?
That's probably roughly the time scale that we're talking about. So, so as you know, for example, the Large Hadron Collider is now doing the run 2
right.
at 13 tera-electron volt.
Mm-hmm.
And I think, so all the results I showed you today are from this run 1, which uses, as far as LHCb is concerned, uses an amount of statistics that is referred to as 3 inverse femtobarn. Now, in the current run, I think they expect to collect an additional 5 inverse femtobarn within just the next year. Mm-hmm. And also at this higher collision energy, the production rate of B quarks is actually higher. Although the backgrounds are also higher. So now there was this outlook plot here at the end showing that. So this is, as you see, so this going up here, this is basically the run 1, and now we've started this run 2, and you see this is by how much the statistics will increase, but also there will be beyond this increase in statistics, actually they always come up with better ways of analyzing the data. It's better algorithms for isolating the desired final states from the background. And so I expect actually even more improvements than suggested by just this curve.
So question back to this.
I have one main question. Like so far we are well familiar with the 6 types of quarks, and hunt for the new particles is still on. So apart from satisfying the human quest for knowledge, and my question is, like what kind of applications can be realized in daily life? Like for this, I mean, how they can be helpful in
Yes, thanks for asking. So, I'm not claiming that these new elementary particles that we might discover will directly have applications, but the nice thing is that nevertheless, this whole search for them leads to many technological applications. So, one of them is progress in supercomputing, which is useful for many big challenges in society. Then, of course, the particle physics has in the past led to many applications, such as medical imaging. The World Wide Web was developed. It's kind of useful, I would say, and it's things like that that come out of this fundamental research, and so already those things make it very worthwhile.
Yeah, so earlier you had this plot where you showed how you were able to predict the masses of particles in your QCD simulation, and different particles had different error bars.
Yes.
And so why are some particles more hard to simulate?
So this is partly because our method is a statistical one. So we do this importance sampling for this path integral, and it turns out that when we do the calculation, certain types of particles are intrinsically fluctuate more around as we do the path integral than other types of particles do. So rather it's the quantum field, the expectation values of the corresponding quantum field operators that we're using to get those masses. Those tend to be more have more variance, more intrinsic variance. That's the main reason why some of these error bars here are larger.
You can't control that in the program. It's just spread.
That's actually physics. We can make some theoretical arguments actually predicting the variance, and so there's an argument by Peter Lepage that would tell you, for example, that a pion at zero momentum would be the cleanest thing that you can have, whereas once you go to a larger momentum, you get more variance, and also once you go to the baryons, for example, you get larger variance. There's a field theoretical argument that actually tells you this, but considering the expectation value of the variance which contains the expectation value of the square of the quantum field operators.
Well, I think we should call it quits here. If anybody wants an explanation about oscillations of K naught and K naught bar, I can give it to you afterwards. You didn't want to do it during the colloquium because it takes a few minutes. But anyway, let's thank the speaker once again.
I also didn't want to speak up there during the colloquium.
So you would be able to take the philosophers. Have you?
No, we haven't met.
Stefan Meinel is Gordon Thompson, one of our supreme considerate physicists here, but also once upon a time, I believe high-energy experiment.
Tenure for an experiment studying CP violation.
So he could anyway, so tomorrow night,